Okay, hi everyone, this is the dimensions presentation, although we will be looking at upper and lower bounds towards the end of this as well. As you can see, I've got a little animation here. We actually call this the hypercube, or a cube in 4 dimensions. It also goes by the name of the tesseract, and it is a lovely GIF image. Now, to be honest with you, the maths that I'm going to be looking at today isn't going to be much to do with the 4th dimension, or any dimension higher than the power of 4, because quite frankly that is well beyond the scope of the GCSE and the A-level syllabus. But if you are interested in that, it is a very interesting topic, and certainly it captured my imagination while studying at university. Anyway, let's take a look at what kind of facts students need to know for dimensional analysis at GCSE. It's a strange topic. It's quite hard to link with other topics. But okay, you can link it to powers and things like that, but you can't really easily link it to many other questions in the GCSE exam. It kind of sits on its own a little bit. But it appears in the syllabus, if you look very, very carefully at the wording, in the following phrase. Change freely between related standard units, e.g. time, length, area, volume, capacity and mass, and compound units, e.g. speed, rates of pay, price, density and pressure, in numerical and algebraic context. That crucial wording, and algebraic context, lets you know that really you're going to have to deal with length, area and volume in quite abstract context, and that is what we're going to be looking at today. Now, why do students find this topic difficult? Because it is a very strange topic, very difficult to get your head round if you've never actually thought about dimensions before. And the questions do often use distractors, which just come in the form of pretty much any numbers which they can use within the question, which have no dimension. They have 0 dimension. That in itself confuses students as well. Let's take a look at area. Now, all the questions in the exam tend to start with the phrase, let P, Q and R, or A, B and C, or any 3 letters really you like, represent lengths. It will then ask you, how can we find areas from these lengths? Well, let's have a look at 7 well-known formulas for finding lengths. We have the formula for a square, rectangle, triangle, and parallelogram, trapezium, rhombus and kite. If you like, just pause the video here and have a think about what they all have in common, because they do have something all in common. Okay, I hope you've had a little think about that. Well, it's simply that each formula at some point involves multiplying a length by another length, or by itself, which is obviously a length times a length. It doesn't matter what formula for area you get, that is always the case. Let's think of a formula which isn't on this page. Let's think of the area of a circle, pi r squared. Well, r stands for the radius, and the radius is certainly a length. So once again, in pi r squared, we've done a length times a length, because we've done radius times radius. This is the case for any formula, absolutely any formula, describing an area. You're going to, at some point, do a length times by another length. So that's the first remark to make. Now, for volume, I don't think it will surprise you too much, and if you just have a look at a few formulas here, the formula for the volume of a cube is the length of the sides cubed, so let's say the side length is s, then we're going to have s cubed. The formula for a volume of a cylinder is pi r squared h. The formula for a volume of a cone is 1/3 of that formula, it's pi over 3r squared h. And the formula for the volume of a sphere is 4/3 pi r cubed. Now, every one of those formulas also has something in common, and that is that you've at some point done a length times another length times another length. Notice that the numbers like pi or 1/3 or 4/3 can be pretty much ignored when it comes down to the similarities between volume formulae. We can ignore them because they are in a sense dimensionless. They don't take you from one dimension into the next dimension, unlike the lengths. Now, we need these key ideas to start proceeding with our dimensional analysis. Let's have a look, before we do though, at dimensions with 2 terms. Now, dimensions involving more than one term are possible, but you need to recognise that when you are adding or subtracting 2 different terms, they must be of the same dimensional order for you to add or subtract them. Now a good example of this is the formula for the surface area of a cylinder. Pi r squared for the circle on the top, a pi r squared for a circle on the bottom, so you'll need 2 pi r squareds, and then you'll need 2 pi r, the circumference of the tin, or whatever it is you're dealing with, multiplied by the height of the tin to give you the curved surface area of the cylinder. And that's why the formula for the area of a cylinder, that's the curved surface area and the areas on the top and the bottom, is given by 2 pi r squared plus 2 pi r h. Now notice that that has 2 terms in it defining an area, and notice also that both those terms clearly define an area, because the first term has an r times an r in it, and the second term has an r times an h in it, and therefore both terms at some point have length times length. That is critical for understanding dimensional analysis. The key thing is you may only add or subtract terms of the same dimensional order. So you can add a length to a length and you'll get another length. You can add an area to an area and you'll get another area. You can add a volume to a volume and you get another volume. But you may not add a volume to an area or a length to an area. And that brings us nicely up to the next slide. If we ever add a volume and an area or anything like that, we have actually been inconsistent. And if they ask you which of the terms represent none of these, then that is always going to be the term which has inconsistency in its approach. So have a look at the following 7 formulas and see if you can label underneath successfully which ones are lengths, which ones are areas, and which ones are volumes, and which ones are inconsistent or none of these, and therefore involve some kind of adding an area to a length or a length to a volume. Pause it and see what you think. So I hope you've had a little think about that. Let's quickly talk about the answers. Well, ABC is length times width times depth. A, B and C could represent the sides of a cuboid. This is clearly going to be a volume. AB over 2, well, that's length times length, so that's going to be area. We can ignore the divide by 2 because it is dimensionless. In fact, that formula, AB over 2, could easily describe the area of a right-angled triangle where A is one side, not the hypotenuse, and B is the other side, not the hypotenuse. So that's definitely a formula, an expression, sorry, for possibly an area. Now the third one is where we come to this point about inconsistency. Pi BC is an area, and A on its own is just a length, and you may not add an area to a length, and therefore that represents none of these. It is neither a length, nor an area, nor a volume. Pi D is clearly a length because pi is dimensionless. AB plus CD is going to be an area because it's the sum of 2 areas added together. Pi times A plus B, well, a length plus a length is still a length, and the pi is dimensionless, and therefore that's going to be just a length. And lastly, BC squared is going to be a volume. So I hope you got most, if not all, of those right. Let's now take a look at a very tricky one. The square root of s times s minus a times s minus b times s minus c, where s is a plus b plus c over 2. This is a question I'd quickly like to ask you, which is, does it represent a length, an area, a volume, or none of the above? Once again, pause the video and tell me what you think. Okay, I hope you've had a chance to decide. Now, this is certainly an area. And let me talk through why it's an area. Firstly, look at the definition of S. S is A plus B plus C over 2. And therefore, S represents a length plus a length plus a length divided by 2. So S is a length itself. That's the key thing to note. Now, if S is a length itself, and A, B and C are all lengths, then S minus A is a length, S minus B is a length, and S minus C is a length, because if you ever do a length subtract a length, you're still in the length world, the world where we have a dimension of order 1, and therefore what we have within the square root is length times length times length times length, which brings us to the power of 4. Now to the power of 4 is the 4th dimension, which is where we see the tesseract coming in and the hypercube. We don't obviously deal with any 4th dimensional stuff at GCSE, but let me ask you a question. if you square root a power of 4, what do you end up with? You end up with squared, and anything squared must be an area. So this in fact represents an area. I wonder if any of you have met this formula before. It's actually Hero's formula. I think it's pronounced hero and not heron, although it is spelt heron. But it's Hero's formula for the area of a triangle. He was a Greek mathematician who discovered that if you've just got 3 lengths for a triangle, you can in fact work out its area using this fantastic formula. Now, I hadn't met that formula till I got back into teaching. I certainly didn't see it at university, and when I saw it, it just amazed me that there was a formula giving the area of a triangle just from 3 lengths. So I thought it would be an interesting one to look at in the context of dimensional analysis. Okay, I hope you enjoyed that discussion on dimensional analysis. Next up is upper and lower bounds. So, upper and lower bounds are actually quite an important topic. They have real practical application and are used all the time in whenever scientific measurements are taken. Because if you take a scientific measurement, you need to know the degree of accuracy with which your measurement was taken. Because obviously it can affect your results if you're later plugging it into a formula. Now, the accuracy you can describe in the words of upper and lower bounds, or error bounds. It is the maximum value your measurement could have taken and the minimum value your measurement could have taken. So, to take a simple example, if my height is 180 centimeters, correct to the nearest 10 centimeters, then what is my maximum and what is my minimum height? Well, if you think about it, my minimum height would be 175 centimeters, and my maximum 185 centimeters, and that is because I said I was rounding to the nearest 10. If I'm rounding to the nearest 10 and my answer is 180, the lowest it could have been is 175 and the highest is 185. Anything within those bounds would have rounded to the nearest 10 to 180 centimeters. Now, if we change it and now say if my height is in fact 179 centimeters, correct this time to the nearest centimeter, then what is my upper bound and lower bound for heights? Well, my upper bound this time is going to be 179.5, because at that point I would have started rounding up to 180. And my minimum height, my lower bound, is going to be 178.5, because at that point I would have started rounding up to 179. So clearly upper and lower bounds have a lot to do with rounding correctly, with decimal places and significant figures. However, it does get slightly more complicated than that. Let's actually use Hero's formula, which we just met in the last part of the presentation. Let's say a triangle's sides are measured and found to be 3 centimeters, 4 centimeters and 5 centimeters, and they were all measured to the nearest centimeter. Using Hero's formula, find the upper bound for the area of this triangle. Firstly, for Hero's formula we need to find S first. Now we need to round all our values up to 3.5, because if they were measured to the nearest centimetre, then each one of them could have been almost as big as 3.5. So 3.5 for the 3 centimetre one, 4.5 for the 4 centimetre one, and 5.5 for the 5 centimetre one. If we now add those up and divide by 2, we get a value for S of 6.75. We can now apply Hero's formula and find the area, and what we will find is the maximum area it could have been using those measurements. And sure enough, we plug those values into our area formula and we end up with 7.8549, correct to 4 decimal places. And that would be described as an upper bound for the area. Sadly, it gets more difficult when you've got fractions in your equation. And that is because you might think that to find the upper bound, you always just take the biggest values for your measurements. But if you think about it, that won't work for fractions. And that's because if we take any fraction, absolutely any fraction, and we want to make it larger, well sure, we need to make the numerator larger to make the fraction larger, but we actually need to make the denominator smaller to make the fraction larger. So the example I use here is 3/5. If I want to make it larger, I can increase the numerator by 1, making it 4/5. That's certainly larger than 3/5. But also to make it larger, I could decrease the denominator to get 3/4. 3/4 is clearly bigger than 3/5 because 3/5 is 0.6 and 3/4 is 0.75. So you must remember, if you're ever dealing with upper and lower bounds and your formulae which you're plugging them into is a fraction, you need to make sure that you're making the numerator larger and denominator smaller to make the overall fraction larger. And likewise, if you want to make the whole formulae smaller, then you need to do it the other way around. Let's take an example, because it's only easy really to see with an example. Here is it's actually an exam question. Katie's driven for 238 miles, correct to the nearest mile, and she's used 27.3 litres of petrol, correct to the nearest tenth of a litre. Now, the question gives us the formula for petrol consumption, number of miles travelled divided by number of litres of petrol used, and it wants an upper bound for the petrol consumption for Katie's journey. Now, a weaker candidate will always just find the upper bound for the miles and an upper bound for the petrol and plug that in. But that is not the way to proceed. Granted, we need an upper bound for the number of miles, but because we're dividing by the litres of petrol, we need to make the denominator of that fraction as small as possible to increase the maximum value of petrol consumption. Because, like I just argued, you make the top of a fraction larger but the bottom of a fraction smaller to find its biggest value. If we're trying to work out the upper bound here, the miles were worked out to the nearest mile, so the upper bound for mileage is 238.5, but the petrol was worked out to the nearest tenth of the litre, and we need the lower bound for petrol, and therefore we want 27.25 for the petrol. Divide the numerator by the denominator and you get 8.75, correct to 2 decimal places. Now, I've never seen upper and lower bounds get any more difficult than that, but certainly if you think, what I often use with my students is the description of a big top, small bottom, or small top, big bottom. They seem to find that quite amusing, I don't know why, but yeah, it often gets the point across anyway that fractions do not work as simply as pretty much any other formulae. Everything else is fine really, you know, if you're squaring or square rooting or anything like that, you'll still take upper bounds for the highest value and lower bounds for the smallest value, but fractions are different and you need to make sure that you go the opposite direction for the denominator. Okay, I hope that's been really useful. It's been lovely to deliver another presentation with you, and yeah, I will speak to you soon in the next presentation. Bye bye.